Hi, hi. Welcome back to Math 234. I'm still your host, Steve Dragu, and today we've got section 16.5 or chapter 16, section 5. Last thing that could show up on exam 3, it's the curl and the divergence. And also sort of a welcome break from the last few sets we've been doing because I think this section is quite a lot easier than all of the triple integrals we've been doing. We're just going to look at two different ways of evaluating derivatives and what they mean in 3 dimensions. So to get there, I want to do a quick review of some older material. So starting with heading back to section 16.3, where we were looking at the fundamental theorem for line integrals, and specifically, I want to look at one of the examples all the way at the end. So here's that example. A conservative vector field, because that's going to play a big role in why we're doing what we're doing today. So remember that a conservative vector field is defined as a field that is the gradient of some scalar function. So a field being a vector quantity. It's got 3 components, an x component, a y component, and a z component. And the gradient, as you might recall, is it's basically a vector valued function where each component is just the partial derivative with respect to that variable. So partial x, then partial y, then partial z. That was our gradient. Here's what we are really trying to say. If f is PQR, so we're just going to give labels to its 3 components, then if it's a conservative vector field, those 3 components are really partial derivatives. F partial x, partial y, and partial z. So that's what we wanted from a conservative vector field. If it's conservative, it has this property. Not all fields are the result of some gradient. So we want to show some stuff. This is the part that we're actually going to get into today, is showing all this stuff in the middle. But I want to jump over that for now because I really want to talk about this part at the end. How do we actually find that function? Right, so it's all well and good to say that, our field is the result of some gradient, but how do we find that original function? And well, if each of those components are partial derivatives, why not just integrate all 3 of them? So that's exactly what we'll do. We integrate each of our 3 parts with respect to the correct vector, and then we just put the function back together again. Let's imagine, each of those components, I guess, are Humpty Dumpty in this example. Breaks into a bunch of different components. But if there is a component like x, y squared, z cubed that depends on all 3 of our variables, that term should show up in all 3 of the partial derivatives. All right, if I look back at the integral lines, the one that's right at the top of the screen, the first term in each of those 3 integrals, y squared z cubed, 2xy z cubed, and 3xy squared z squared, all 3 of those terms are really just x, y squared, z cubed, but with a different partial on them. Right, first it's the x partial, then it's the y partial, and it's the z partial. I think it's easy to pay attention to the coefficient because you can see that that's the number that got brought down when I took the derivative with each one of those individual pieces. Main reason I'm highlighting that is because when I put my function back together again, I only need that term to show up one time. Because that one term will split into each of the 3 partial derivatives. So I don't need it 3 different times. In fact, it would be wrong if it were 3 different times, because I'd be off by a scalar multiple. So I only want to put it back in once. Similarly, I can look at the xy term, so follow the green line that's on the screen right now. I have the term xy that shows up in both the x integral and the y integral, the dx integral and the dy integral. Because if I look back at the original functions, In the x partial, I just have a plus y, which integrates to xy. In the y partial, I've got a plus x. It integrates to xy. Again, I only want to put it back in the function one time. That one term is responsible for both partial derivative terms. And then for the rest of it, each one has a plus one, but those all just integrate to x, y, and z respectively. So I've got to put each of those in the function as well. All right, so when we're reconstructing our original function from its partial derivatives, we just need to pull out each unique piece from all the integrals that we do. And then as a quick check, the thing that we would have been doing back before what we learned today is that if I took the gradient of this function again, I return to my original field. All right, so you can verify just doing a gradient on that function, and you'll see you get exactly what's right there. So that's what we're going to do today, is reconstruct these functions. Though really we just looked at an example of how to do that. So more we're going to look at when are we allowed to reconstruct that function? Or rather, when can we? It's not a matter of being allowed to or not. It's about whether we can. And one last bit of review, all the way back to chapter 12, like that very first week of the course. I just want to remind ourselves of what the cross product is. So we're doing cross products again. It kind of came up last week when we were doing change of variables. We a little bit needed the cross product when we were doing Jacobian calculations. In two dimensions, that cross product is just a 2x2 determinant. But if we're doing the three-dimensional cross product, then it's a three-dimensional determinant. Again, pretty similar to what we were looking at in change of variables, where, again, yeah, you just multiply down the crosses. Cool. So again, yeah, that's our cross product. It's going to come back up again in a rather significant way right now. So back to the stuff that we have on today. So starting with the new term that we're going to introduce, which is the del operator, or vector differential operator, upside down triangle. Again, we call it del for short. And it's defined as the three-component vector quantity, partial x, partial y, partial z. And again, we've seen that before because that's going to be the gradient operator. Right? If we just multiply that into a scalar function, it creates a vector-valued function that's just partial derivatives in order. But we want to introduce two new operations. Since the gradient only works when it's applied to a scalar function, I want to look at applying this same operator, the del operator, but to vector functions now. So I can't take the gradient of a field, so that doesn't really work. A field is the result of a gradient, but I can't take the gradient of a field. Instead, I can use the del operator in two ways, because we have two different types of multiplication in vector quantities. One of those is the cross product, the one that we just reviewed a second ago. The other is the dot product, and we'll get to that one second. But for starters, we're going to look at the curl of some field F. And it's just the cross product of the del operator with our field, PQR. So we write out our 3x3 determinant that we need to take the cross product of ijk across the top row, our partial derivatives across the middle row, and then PQR across the bottom row. And you get that super fun looking vector function. R partial y minus q partial z for the first component, p partial z minus r partial x for the y component, and q partial x minus p partial y for the third component. And I want to stop to talk just briefly about the third component, because I think that was familiar. Ignore the first half of this note down at the bottom where it talks about Green's theorem and circulation at a point. That topic is hard, so we're going to talk about it Friday. So we haven't actually talked about it yet. So yeah, don't worry too much about that part. But the second half of this note, I think, is important to look at. Qx equals Py, or Qx minus Py equals 0. When we were doing the conservative field test in 2 dimensions, we were asking whether or not we could apply the fundamental theorem for line integrals. This is the test we were looking at. We were looking at if Q partial x and P partial y were equal to each other. And that same piece comes back up inside of the curl, but it's now only one of 3 components because we now need to step this thing up to 3 dimensions. So we've got to look at more than just the one piece here. So we'll glance over here to the right for a second. See if there's anything else I want to talk about. I was already starting to mention this bit at the beginning, but again, we have our del operator. We're going to use it in 3 different ways. We just talked about the first 2, the gradient, the one we already knew, that operates on a scalar function and has a vector output. The curl, again, one that we just talked about, applies to a vector function and gives a vector output. And then the divergence, which we'll look at in a minute, but it's going to be the dot product, and it's the simplest of the 3. Vector function is an input, but outputs a scalar. But all right, we'll return to that idea in a minute, I think. One other thing that I want to say about calculating this curl is that there is an order to all of the letters inside of that curl that I find is helpful for remembering what the thing looks like. Because trying to generate the curl on the fly goes wrong not infrequently. It's easy to screw up the arithmetic or just the simple algebra on this curl because it's got 6 different terms, and each of those terms needs to be paired with a specific derivative. So again, can be easy to mess some of this stuff up. So let's talk about how I remember the curl, the order that it goes in. PQR goes across the bottom row. Everything that goes across the bottom row ends up in its opposite order because of the way that cross products work. Right? When you come back and cross multiply in the backward direction, you end up with a negative attached to it. Right? We've seen that when we've done the cross product. So it's helpful to remember that P, Q, and R, because they're on the bottom row, they go in reverse alphabetical order. So RQP, RQP, right in order. So those elements of the field, again, reverse alphabetical order when going through the cross product. And they go exactly in that order. X and Y and Z, the partial derivatives, they're in the second row, so they all go in forward alphabetical order. But before I talk on that, I need to introduce one other element or point out one other unique thing about this curl. And that's that each component of the curl has no dependency on its position. So what do I mean by that? If I look at the X component of the curl, it's the first component of the curl, it has no information about P or partial X, which are the elements that would normally go in the first component, right? P is supposed to be the X component of our field, or it's the first component of our field. Partial X usually gets the first position in that XYZ order, and there's nothing to do with X or P in that first component of the curl. Same thing applies to the next 2 components as well. The middle component normally is Y, but it doesn't have any Y derivatives, and it doesn't have anything to do with Q. Q and Y are both absent from the middle component. Same thing with the third and final component, Qx minus Py. No dependency on Z. There's no Z partial, and there's no r partial, or there's no r at all, right? R showed up in the first and second components, but not in the third. So each element doesn't show up in its own position with the curl, right? They all get scattered to the other two places. Also, another handy way to check that that's working, in addition to an individual element not ending up in its normal position, it also won't match up with its own partial derivative. So P is the X component. We're not going to take the X partial of P anywhere. P gets a Z and a Y partial, but not X. Q, being the usual Y component, does not get a Y partial, doesn't match up with its own piece. It gets a Z partial and an X partial, but not Y. R, same thing, Y partial and an X partial, but no Z partial. So nothing matches up with its own position. So when I say then that X, Y, and Z all should go in alphabetical order, I can't start with X because I'm starting in the X position. So I've got to start with Y instead. So again, you can't put X in its own spot. So it starts Y, then Z, Z, X, X, Y. All right, so they just go in order. Y, Z, X, and then back to Y. Y, Z, Z, X, X, Y. Okay, cool. So that's my spiel on remembering that. We're going to see if it comes together in just a second. So one more quick look at deciding if a field is conservative. And as it turns out, we're going to get a fancy formula. All right, so remember that for a two-dimensional field, we just needed QX equal to PY. Or to say that another way, QX minus PY needs to be equal to 0. And if we keep that logic going, or we keep that process going, we'll get that each of the three components of the curl need to be 0 in order for a three-dimensional field to be conservative. I skipped over there it is. That's what I was looking for. It was your turn. Yeah. If a field's going to be conservative, the curl must be equal to the 0 vector. So 0 in each of its three components. And the reason for that, if I come look at one other element, remember that if a field is conservative, then it should be the result of some gradient, which means that we already have partial X, partial Y, and partial Z as the three components of the field. And then I'm just going to apply a curl to that. So another set of derivatives on a thing that's already had a derivative done to it. This is our guiding principle for the curl being equal to 0, implying that a field is conservative. Because then when I start to match stuff up, I should see that each component, each of the three components of the curl, is the difference between a couple of second-order partial derivatives, but the position that it's in, that partial doesn't show up there. So the partial of the position doesn't show up in its usual position. So all of the non-X partials end up in the first component, the non-Y partials in the Y component, and the non-Z partials in the Z component. Take their difference, I should get 0 because it's just the same thing for both terms. So that's our guiding principle for why this curl check should work. But then we can actually take the curl and we'll hopefully find that we get a result. Again, to figure out what that original function should have been, I just integrate each piece. Although this function is almost too simple to really see much detail in it. It's just got one term. It all integrates to the same thing. So x, y squared, z cubed. In the example I started with, we just, again, had that first term. But keep in mind, this is some integral that we're doing. So even if we do compare all three components, there could still be a constant term that we would lose all information about. The curl or derivatives in general being a destructive process. Anytime there's a constant term, we lose all information about it when we actually take a curl or a derivative in some way. So that's why I included an extra little constant term there. So after all of that, the divergence is very, very simple. It's just the dot product of that del operator with our field. So p partial x plus q partial y plus r partial z. Again, very straightforward. Just go down the line. Do the derivatives in the order you'd expect them. So we're going to spend most of our time looking at the curl because it's the one that requires a bit more work to understand. But all right, before we move on to an example, what in the heck do these things even tell us about a field? Because we know what a derivative does, right? So if we take a derivative of just some scalar function back in Calc 1, we said it's the instantaneous rate of change at any point on that graph. So what's it going to mean for a vector field? And a couple of things. Start with the divergence again, because I think it's the easier one. If we're looking at some field out in space, gets represented by a whole bunch of vector field lines, right? Like down here, that's an example of a vector field. Each point in space has some vector associated with it. For the divergence, it's a measure of how many of the lines are going out versus going in, right? So we're looking at, is the field converging? Is it coming into the point? Or is the field diverging? Is it going out of the point? Hence the divergence. And since it's the divergence, the positive direction would be going out. We want to be diverging from the point if it's positive. The opposite of that being converging. So that'll be the negative direction for the divergence. So we don't call it the convergence, it's the divergence. So out is going to be the positive direction. In is the negative direction. And if our divergence is 0, that means we have an equal number of lines going out as we do going in. Or it might mean that our lines aren't going out or in at all. Maybe they're just circling around our point. Is another option for the divergence being 0. Speaking of circling around the point, that's kind of what curl sounds like. And that's what it is. So the curl gives some sort of a description of how the field rotates around a point. Counterclockwise will be our positive direction. Counterclockwise will be our negative direction. So those are our two rotation options. And if the curl is 0, that means that the rotation is balanced, or there's no rotation at all. So if we maybe look at this blue option over here on the right, if all our vector field lines are straight, if it is passed straight through, then that's a curl of 0. So those lines aren't curling, they're just going straight. We should probably also mention that the outputs of these two operations are in different spaces because the divergence just gives a scalar value as its output. Right? I take the divergence of a function and I just get a number. It's very easy to talk about it being positive or negative. But for the curl, its output is a vector. Less easy to talk about it being positive or negative. We can definitely give positive and negative orientations to the spin because that's one of two directions, clockwise and counterclockwise. But when we say the curl is positive or negative, we're really trying to talk about this pink vector right there. So if my rotation is swirling around in that blue plane, or that's the direction that things are rotating in, then the curl points in the direction, again, of that magenta vector. And since we're really fond of right-hand rules when we start thinking about 3 dimensions, there's a right-hand rule for this too. So take your right hand, curl your fingers in the direction of whatever your rotation is. If you do that, so it's something kind of like this. Again, it should look curled. I kind of just move my hand around. Your thumb points in the direction of the curl. Again, the curl being a vector. So if we do this example that's on screen, curl your fingers in the direction of those blue curled lines. Your thumb points in the direction of the curl. So if we're just in the XY plane, you can't see that. Just in the XY plane, yeah. Stick your hand on some flat surface. The curl is going to point straight up. So in the XY plane, it's a lot easier to talk about the curl being positive or negative because we can say it's positive if it points in the positive Z direction, or it's negative if it points in the negative Z direction. So if I'm swirling counterclockwise, my thumb must point down in order to make that happen. But all right, now I think we've got enough information to do some examples. Yeah. So consider the picture over to the right. We want to decide if the following value should be positive, negative, or zero. And then we'll actually calculate some stuff to validate our guess. So we're looking at the divergence and the curl at 1, 1. So first off, let's go mark 1 on the map. So the point in question is right here. That's 1, 1. Trying to decide if let's start with the divergence. Is this thing going to be positive or negative? Mostly all of our lines are just pointing to the right if we're at that point. There is some curling action going on, but we'll talk about that in a second. For deciding if I think the divergence is positive or negative here, well, I want to figure out if the lines coming out of this point are longer or shorter than the lines coming into the point. And so if I look over here to the right side of the point, right over here, I see relatively short vector field lines. But when I look over to the right side of the point, I see my lines are relatively long, right? My lines on the right side are longer than the lines on the left side. And the lines on the right are pointing out while the lines on the left are pointing in. It's pretty much everything is moving to the right at this point. So since I've got larger lines on the right than I do on the left, I've got larger lines out than I do have in, I think that this is going to be positive. So positive for the divergence. For the curl, it helps to kind of take a bit of a more step back approach to kind of figure this one out. If I look at the field as a whole, it looks like it's got a center at the origin, and then everything is kind of swirling clockwise. Right down here, I'm kind of going this way. I'm definitely going this way. Kind of going that way. Kind of I'm going that way. Right, as sort of a very broad approach to this field, everything's kind of going a bit clockwise. In particular, at our point, I can see that same idea is showing up. Kind of moving that way. So this would be clockwise. Which means that I'm going to expect my curl to be negative. All right, and then let's check those answers. Starting with the divergence, because again, I think it's the easy one. Divergence of f. I just need partial x plus partial y. Partial x is 1. Partial y is 1. I get 2. Right, because remember, we'll be taking those partials in order. Now, the curl. When we go to calculate that thing in 2 dimensions, we only really have our curl defined if it's a 3-dimensional vector field. So if we're trying to apply the curl, we need 3 components. But our field only has 2. So we just need to extend the field into 3 space, which we'll just call PQ0. Because then I can apply the curl to that thing. So the curl of f is going to be 0, 0, something. So that's another fancy bit about going to the curl in 3 space, or in, sorry, back that up. The curl of a just XY plane, a 2D space, if we're working just in a plane, in a 2D plane. The curl will have 0 for both its X and its Y components, and then only a Z component. All right, you think about, swirling, taking that curl being in the XY plane, our vector must point in the Z direction, either straight up or straight down. When you multiply this stuff out, you'll find that in the first 2 components, everything has to get multiplied by 0 because of the position of that third option, of that third thing we're multiplying in. But moving on, that third piece should just be QX minus PY, which is going to be 0, 0. QX is going to be -1 minus P partial Y, which is going to be +1. And then I can see that that vector works out to 0, 0, -2. That's my third curl. If the curl's not making sense just yet, because that would be totally fair, it's kind of a weird thing to put together. Wait just a second, because we'll look at a curl in a full 3D example in a second. And that's when I really want to dive into the meat of it. Yeah, okay. Going over one more field example. So introduce a new field, but this time we'll be at the point 3 pi over 2 pi, which will be that point right over there. And again, look at the curl and the divergence. So this one is swirling quite a lot. And if I just look locally right around our point, it's going counterclockwise this time. I can see a lot of counterclockwise rotation. So the curl here is going to be positive. Again, it's going counterclockwise. But the point I've picked is right at the center of this rotation. Everything sort of seems like it's swirling around our point, 3 pi over 2 pi. So the divergence will be 0 there. Because none of these vector fields are pointing out or in. They're all going around that point. So I think that 0 for the divergence and positive for the curl. So we just go calculate that thing. Divergence of f. Well, sine y partial x is 0. And cosine x partial y is also 0. So nothing for the divergence. Which means at any point in this field, the divergence is 0. Not just the point at our center, though it's pretty easy to look at the center and say it doesn't have any divergence. Curl will be the fun one, though. So the curl of f. Again, it's in the xy plane, so we won't have any dependencies on, we won't have any values in the x or y direction for the curl. It all points z, either up or down, and we need a derivative of those pieces. Again, this is qx minus py. So q partial x, that's the derivative of cosine x, or rather cosine x partial x. That should, come back here. That should be negative sine x minus p partial y. So sine y partial y is cosine y. So then we just should plug in our points. We have 3 pi over 2 for x. So the sine of 3 pi over 2 is negative 1 minus. Oop, I left a negative off, didn't I? That's negative 1. There we go. Minus cosine y. Y is pi, and the cosine of pi is also negative 1. So negative 1 minus negative 1 is really 1 plus 1, or 2. So again, clockwise rotation should come out to a positive value for the curl. As long as we're in 2 space, there's just a 1 component that shows up in the curl. Couple of extra definitions. Again, curl should talk about whether or not something is rotating around a point. It can be helpful to think of curl and divergence in terms of some fluid dynamics. For anyone in engineering, I'm sure you'll become intimately familiar with those ideas. But if a curl comes out to 0 at a point, we'll call it irrotational at that point. And if our divergence is 0 at a point, we'll call it incompressible at that point. So we can just check curl and divergence of this field. And it's a decent enough place to start our curl adventure. So let's do that one. First off, the divergence of this field. Negative 2x partial x is negative 2. Negative 3y partial y is minus 3. 5z partial z is 5. Add all those up and we get 0. Right? Divergence is just straight down the line. Then to get the curl. Again, to remember our order. P, Q, and R always go in reverse alphabetical order. So this is R, Q, P, R, Q, P. And then our partial derivatives go in the normal alphabetical order. So y, r partial y minus q partial z. Then p partial z minus r partial x. And then q partial y minus p partial x. Oop. Set all that, and then I got them backwards. Q partial x minus p partial y. So let me actually back up to the spot where I made a mistake and mention how I knew that that had to have been wrong. Right? So I tried to apply my thing. Again, it's pretty easy to mess up one of the individual elements here. But looking at that third piece, again, I know it's wrong right away because I cannot pair any two elements from the same column in that curl. So Q is the y component. I can't pair it with the y partial, but that's what I did in that third component. Same thing with P. It's the x component, so I cannot pair it with the x partial, or rather, I shouldn't pair it with the x partial. So when I looked at those and saw that y got paired with q and p got paired with x, I knew that I had made a mistake. So that's where I go to correct that last piece. Say q partial x minus p partial y. So again, that's why I think that those elements can be helpful of remembering alphabetical order and also the way that things get paired together. So they can help you sort of self-correct when you're doing one of these problems. But we'll see on this example that it's actually kind of boring each way through because each component depends only on its own variable. So r partial y, r is that one, q is that one, p is that one. 5z partial y is 0. 3y partial z is 0. 2x partial z is 0. 5z partial x is 0. 3y partial x is 0. And 2x partial y is 0. So not a ton of interesting things going on, but it does mean that the curl is 0 everywhere. So the thing is irrotational. And we saw in the beginning, the divergence was 0, so it's also incompressible. This thing is both of those two new elements that we just added in. Two new definitions that we added. All right, so let's go do some stuff. All right, well, this one's fun because these are Ryan's notes. So, your friend Ryan comes up to you and is like, whoa, you have to check out my awesome vector field. You know what? But you can't even figure out what it is. Only thing I'll tell you is the curl of f is the curl that's provided there. Shut Ryan up by finding his vector field, if it exists, or prove Ryan is not being honest with us. So somehow works even better when Ryan's not here. Right. So he told us the curl of his field. And we need to either prove that he wasn't honest or find his field. First off, if we did have to find his field, I don't think we could do it because that field could always have a constant term in it. And there's no way for us to find that constant term without there's no way for us to find that constant term without some extra information. So if we had to find the field, we'd be in trouble. There'd be nothing we could do. Which makes me think he's probably not being honest. So, fortunately, there at the top of the screen, we have an option, or we have a definition about mixing the curl and the curl and the divergence together. And that's if we do that, we should always get 0 for any field. So we can check that on Ryan's field right here. xz partial x is z plus xyz partial y is xz and negative y squared partial z is 0. And I can see pretty clearly that that thing is not 0. meaning Ryan's not honest. Ryan is not being honest with us. Not being honest. Mark that off in red. Not being honest. A very quick sketch of why that should be true if we mix the curl and the divergence together. If you just expand out both of the terms, curl is there. It's a thing we've seen a few times. The divergence is just apply the x partial to each piece. Looks very similar to that conservative field check, except that everything adds together to get 0. So now each individual element doesn't need to be that way, but all together, if I add them up, I should see 0. But all right, right. We know that that's false. That was just the same question. So finally, let's calculate one curl for real. So the curl of F. Again, RQP in reverse alphabetical order. And then throw the partial derivatives in their correct alphabetical order. Y, Z, Z, X, X, Y. So that's the bit I'm after. And then I can calculate this stuff as we go. So R, right? That one's the third one. Q is the one in the middle. P is the first one. R partial Y is X minus 1 minus Q partial Z, which is X plus 0 plus beta. Then P partial Z. So looking at that first term, do its Z partial. I get Y, and that's it, minus, where did we go? R partial X. So look at the third term. I get Y minus 0, so just Y. And for the third term, Q partial X, going through that guy, I'll get Z plus 3 plus 0 plus 0 minus P partial Y. Look at the first term. Partial Y. Ooh, no, my pen has decided to stop working. Convenient since we're over on time, like usual. But if I look at that third one, the last or the sixth piece that I'm missing, P partial Y, I should get Z plus alpha plus 0. Z plus alpha. There we go. And I know that that thing, if it's conservative, has to be equal to the 0 vector, in which case I can solve for each of these pieces together. This looks like -1 plus beta is equal to 0. 0 equals 0. And 3 minus alpha equals 0. And then I can solve for beta and alpha. Beta needs to be negative positive. That was a minus beta. There we go. Beta needs to be -1. Alpha needs to be 3. The middle term 0 equals 0. That part was already good for us. So we found our missing components. The last bit that I will add in later was reconstructing the field, but we kind of talked about that right at the beginning. So I'll leave that alone for now. But here's the work. Just integrate each piece, put your function back together. All right, so that's it for here. I will see you guys again on Wednesday when we're reviewing for the final. Should really stop talking. We'll be reviewing for exam 3, which is this week. It's not the final exam. Okay, bye, 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 bye. Bye, 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 bye.